Stripping down science. The Naked Scientists.
Hello, it's Sunday, September the 19th, and this is The Naked Scientists. I'm Ben Valsler. This week, we're bringing you some of the highlights from the British Science Festival, including exploring the history of pi, and that's the number, not the food. Joining me for the news this week is Chris Smith. Hi, Chris.
Hello, Ben. Well, also in the news this week, how scientists are using the pattern of craters across the moon's surface to reveal how the solar system ended up the way that it has, and also why street lighting could spell disaster for birds' breeding habits. That's all on the way.
Thanks, Chris. And Dave Ansell will be here with me for the rest of the show.
Thanks, Ben. We're also bringing you the first edition of Naked Engineering. I join Mira Senthilingam to strip away the image of dirty overalls and find out how engineers solve problems. This week, the power of the arch.
That's all to come on today's Naked Scientists, and if you've got any science questions or comments, we'd love to hear from you. If you want to contact us through Twitter, all you need to do is tweet at Naked Scientists, or our email address is chris@thenakedscientists.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
This is The Naked Scientist with Chris Smith, Dave Ansell, and with me, Ben Valsler. As always, let's kick off with some science news. Dave, what do you have for us this week?
Now, one of the most obvious things about the moon, if you ever looked at it through a telescope or even just a pair of binoculars, is it's covered with craters. But these aren't uniform. Some older areas called the highlands of the moon are very heavily cratered, whereas the mares, thought to be seas by early astronomers, have fewer craters. This is because the mares have been resurfaced with molten rock more recently, and this shows that the number of impacts has reduced over time. Now, one quite controversial theory about these craters says that there's an event called the Late Heavy Bombardment about 3.8 billion years ago, which was both far more intense than the later bombardment, and it was qualitatively different. There were different rocks coming and hitting us. Now, going and dating each individual crater and with an actual object or a rover is ridiculously expensive. However, the Lunar Reconnaissance Orbiter, which was launched last year, includes a laser altimeter, which has built up a 3D map of the moon. Now, James Head and colleagues have been studying craters over 20 kilometres using this map. One result was that in the lunar highlands, the craters cover 3 to 10% of the landscape, which is effectively the highest you can ever find, because as new things come down and create craters, they're erasing older ones. They've also been comparing different age surfaces. The younger ones have a distribution of crater sizes you'd expect from the asteroids which are presently crossing the Earth's orbit. However, the older highlands, dating from before this late heavy bombardment, seem to include far more large craters than they should. This indicates the late heavy bombardment wasn't just a more intense version of the bombardment which has occurred ever since, but something actually different. One theory is that the orbits of Jupiter and Saturn have changed during the early years of the solar system, and this set up a resonance in the main asteroid belt, disturbing it and hurling a random selection of its contents into the inner solar system. And this could have huge effects on developing life in the early Earth.
So the evidence for this on Earth is likely to have been wiped out by the fact that Earth is very geologically active. It recycles the crust quite frequently. Do we see evidence on Mercury and Venus that this late heavy bombardment happened and was what we think it might be?
There's definitely evidence for this very, very heavy bombardment on both Venus and Mercury. Better on Mercury, of course, because Mercury doesn't have an atmosphere, whereas Venus has got a very, very thick atmosphere. But there is evidence for this late heavy bombardment everywhere, but no one's done quite this sort of study on them.
And the bottom line then, Dave, is presumably that what we used to think was that a random selection of asteroids came out of the asteroid belt and smashed into us. Now we can actually say, well, at one time in history, they were one size, and then in a subsequent phase of history, they were a different size. So this is kind of rewriting our understanding of the formation of that asteroid belt and where the giant planets actually went during the history of the solar system as they took up their final positions and dislodged these objects.
That's right. They think that all of the more recent asteroids which have been dislodged from the main belt tend to be smaller because it's done by things like light pressure from the sun, which affects smaller asteroids more than bigger ones. So you get a different distribution of impacts.
It's amazing to think that these footprints written into the moon's surface retrace the movements of the giant planets all those billions of years ago.
Indeed.
And we've discussed a lot more about the history and the migration of different planets throughout our solar system in the Naked Astronomy podcast. You can find that at thenakedscientist.com/astronomy.
Ben, what have you got for us?
Well, from shedding light on the history of the solar system to shedding light on birds at the wrong time, it looks like worsening light pollution is significantly affecting bird breeding habits, according to a new study published in Current Biology. Bart Campeneas and his colleagues at the Max Planck Institute for Ornithology in Seewiesen in Germany has carried out a 7-year study comparing the behaviours of 5 different songbird species, all ones that should be familiar: robins, blackbirds, great tits, blue tits and chaffinches. And they either lived in dark central woodland areas or in light-contaminated edge territories. This is still woodland, but where light falls on it from local human habitation. Male birds living in the light-polluted areas, they found, were starting to sing significantly sooner in the day, in some cases up to 2 hours earlier in the morning. Now, this is significant because the dawn chorus doesn't just consist of all the birds waking up at once and singing. It's a very finely layered, almost musical composition. Now, they were singing 2 hours earlier than their darker living counterparts, who still sang when the sun came out as normal. The effect was also more marked amongst the species that naturally tended to wake up earlier in the morning anyway, so the first ones in the dawn chorus, such as robins and blackbirds. Females exposed to light pollution were also laying eggs an average of 1.5 days earlier. The team also found that males living in the lighter edge territories were twice as likely to father extra pair offspring, and these are the avian equivalent of love children, probably because they won more female attention by starting to sing sooner than their darker living rivals. However, since females usually select as their extra pair mate choices males that they perceive to be highly reproductively fit, basing their selection on dawn song as a measure of virility, the early male risers may be thwarting the selection system and fooling females into breeding with the wrong guys, the less fit guys. And this can have obvious negative consequences for the species as a whole.
Doesn't sound that serious, though. 1.5 days of earlier egg laying. Do we really think this is likely to have an impact on the birds, and why?
Well, this sort of thing is really very hard to tell because ecosystems are usually very finely balanced and different food sources will be available at different times. So if we have a burst of bird birth a little bit earlier than normal, then there may not be the food there to feed them. Or there may be plenty of a different source of food that they don't normally eat. This can have knock-on effects on other species in the area. And all in all, the ecology is actually fairly finely balanced on these sorts of timings.
So what do the researchers propose we do about this? Just turn the lights off?
Well, humans are going to need lights, and we know that having road lights makes things a lot safer, so it's really not as simple a situation as just turn the lights off. But it's certainly worth keeping an eye on to see if this does have any ecological impact, and to see if there is something we can do to try and supply darker areas and contiguous dark areas where the species can behave as they would do naturally.
Well, let's hope so. Thanks, Ben. Well, also this week, in a move which might hold the key to better drugs that can beat a range of mood disorders and perhaps do it with fewer side effects, and I'm thinking of diseases and disorders like depression, researchers in France have fathomed out how one of the most commonly used antidepressants, and best tolerated, that being Prozac or fluoxetine, actually works. Now, going back about 50 years, we've known for that long that people who have problems with their mood and are depressed, if you study the brains of those people, you find very low levels of a chemical called serotonin, 5-hydroxytryptamine, which is one of the nerve transmitters that nerve cells use to talk to each other. In effect, it's the brain's feel-good chemical. So, most drugs now work by elevating the levels of serotonin, or so we thought, because there's the problem. When you give people antidepressant drugs, you can measure the effect on their serotonin in the brain almost immediately. The levels go up. But people say they don't feel better for maybe 2 or 3 weeks after starting the drug therapy. So the elevation of the levels of serotonin can't be the whole story. And that's where a group of researchers in France come in. It's Anne Baudry, who's at the University of Paris-Descartes. And what she and her colleagues are publishing in the journal Science this week is a very interesting insight into actually how drugs like Prozac do what they do. They were using cultured cells in the dish, and also they were using rodent brains. They were injecting and adding Prozac into the brains to see what would happen. And what they find is that when you expose nerve cells or nerve-like cells to fluoxetine, Prozac, they reduce their expression of a reuptake transporter. Now, this is a special chemical which sits on the surface of the nerve cell, and it acts like a vacuum cleaner for serotonin. It pulls serotonin back into the nerve cell, reducing or negating its action. Now, what they found was that when you take fluoxetine, you switch off the production of those particular transporters. And the way they found that this happens is that the Prozac turns on a small functional RNA molecule called a microRNA. In fact, it was called microRNA 16, and this gene is the genetic mirror image of the gene that makes the reuptake transporter. So one cancels the other out, and you stop making these transporters, and so the amount of serotonin that comes out of the cell goes up, and it stays in the brain for longer, and therefore it makes people feel a bit better. But there's an added twist. They also found that the drug makes this same population of nerve cells secrete another chemical signal called S100 beta, and it goes on to a second population of nerve cells which use the nerve transmitter chemical noradrenaline. And when it goes into those nerve cells, it does the reverse. It turns off this microRNA 16, and that means that these noradrenaline-using nerve cells now start to express the uptake transporter for serotonin. And before long, these noradrenaline-producing nerve cells are also using serotonin. So they're secreting serotonin alongside their noradrenaline normal transmitter. So what's happening in the brain is two things. One, you're increasing the amount of serotonin signal in the brain, but the other is that you're turning another group of nerve cells that normally use one transmitter into a combined sort of dual-use nerve cell population that use two transmitters. And they think this probably underlies the therapeutic ability of Prozac to make people feel better. The important take-home message here is that it's a new insight into how these drugs work, and understanding that molecular clockwork may mean that we can design better drugs which are more highly focused, able to achieve their effect faster and with fewer side effects.
Does this mean that we can find a way to stop the problem that people have when coming off antidepressants, which is that you need to reduce the dose very gradually over quite a long time? Otherwise, the side effects can be quite severe.
Well, they may have a better withdrawal effect profile, but it may be that you don't actually get dependent on them in the first place. It may be possible to engineer more effective antidepressants which will act more quickly, more discreetly, and without fewer dirty actions which are peripheral to the actual beneficial therapeutic effect. That's the hope, although it's early days.
Well, there's some other news about Prozac this week that's come out at the British Science Festival, where I have been all week. And now I'm just going to take you through a few of the headlines that we've had. Thelma Lovick, a researcher at the University of Birmingham, announced that very small doses of Prozac can stop the bodily changes that result in the symptoms of premenstrual stress. May sound like a fairly casual thing, but premenstrual stress affects up to 75% of women, and in 30 to 40% of those cases, it's a strong enough problem to impair daily activity. So that's some interesting research. There's been something else from King's College London. Richard Smith announced the development of a technique that extends the lifespan of a transplanted organ by combating the immune attack that donor organs receive immediately after transplantation. Now, their trick is to tether these immune system modulating chemicals onto the surfaces of the kidney, and that stops this complement cascade, this immune attack, in its tracks. They've done a pilot study to show that it was safe in 16 patients. Obviously, they're going to scale that up. King's College again, this time Dr. Manuel Mayer has announced a cheap way to test people for diabetes risk. It's a £2 blood test that looks for microRNA markers in the blood. It was able to identify around half of the people with type 2 diabetes before symptoms develop, which widens the possible treatment window. Now, as diabetes accounts for around 15% of heart attacks in Western Europe, that's a very, very important discovery. Dr. Mayer suggests that we use this not as an exclusive test on its own, but in concert with all the other methods we have. Just for headlines, we heard that gaining a lover will cost you 2 friends. The Pope's astronomer dropped by to let slip that he's a science fiction fan and that the Catholic Church would welcome aliens should they discover them. And there was also an announcement that might seem to come from the School of Common Sense, and that's that 1 in 10 people are quite likely to be injured whilst walking and texting. Also during the British Science Festival, researchers from Bristol University reported on a development in quantum computing that could bring this revolutionary technology closer by up to 20 years. I met up with Jonathan Matthews to find out how their device works, but first, Jeremy O'Brien, the director of the Centre for Quantum Photonics, explained why quantum computers are so appealing.
People have been trying to develop a quantum computer for at least a decade in a serious way, and for a couple of decades people have known that such a device could be incredibly powerful for computation for particular tasks. And so there's been a big worldwide effort to realise a quantum computer. Even at this stage, it's anticipated to be decades away, and the reason for that is that you need to be able to control single quantum systems, so that could mean single particles of light, single photons or single electrons or single atoms. You need to be able to couple them together in complex ways to control them and manipulate them and read out the state that they're in. So it's an incredible quantum engineering challenge, if you like, to be able to make such a device. There's tasks that we know that we can do with a quantum computer exponentially faster than we can do with a conventional computer. So that means we can do problems that are intractable on a conventional computer, and they're ones whose time taken to do the computation grows exponentially with the problem size. For a quantum computer, we don't have that. They're linked in a sensible way with one another, the size of the problem and the time taken.
So rather than an evolution of the existing computer, we're looking at a revolution of the sorts of technology we use.
That's exactly right. So it's a completely different way of doing computation, and the idea is to harness uniquely quantum mechanical effects. So quantum mechanics is the theory that explains how the world works at its most fundamental level, how single photons, single atoms, single molecules and so on behave and interact with one another. And it's surprisingly different to the way the world works in our everyday experience. For example, it tells us that an object can be in two places, or more places indeed, simultaneously, that two objects can be inextricably linked with one another no matter how far apart they are, such that a measurement on one will instantaneously affect the other one. And we call these effects superposition and entanglement, but that's essentially what they are.
Jonathan, if I could bring you in here, what physically is this device that you've developed?
This device is an integrated optical chip. It uses what we call waveguides to guide light through a monolithic structure, through a fixed structure. And these waveguides work very much like optical fibers, like pipes for light, if you will. And what we do is we pattern several of these waveguides close together so that the photons can actually tunnel directly between neighboring waveguides or neighboring pipes. And this allows us to see these superposition patterns that we call quantum walks.
What is a quantum walk, and how would it differ from a classical walk?
Perhaps I can start with a classical walk. A classical walk you can realize by dropping a marble and giving it a series of choices by going left or right as it hits a bunch of pins arranged in a grid pattern. And this will give you a normal distribution at the bottom, a bell curve. So that's based on the marble being given a choice of going left or right based on probability. But if you give the marble the possibility of going left and right, it has the possibility of interfering with itself, and you get at the end a very different statistical outcome. These statistical outcomes include features such as propagating much faster. The distribution propagates much quicker than in the classical case. And it's this kind of behavior that can be really harnessed in quantum technologies.
So a quantum object will give you a very different likelihood of landing in any particular place from this walk. And that's when you put one photon through. Your work is working on putting more than one through to see how that works out. What's the advantage of doing that?
A key thing is you need the two photons to be exactly the same in every single property, but they quantum interfere with each other. And the fact that there are two photons gives you a different statistical output that if you put in one photon and then put another photon in and compare the two results.
So in terms of quantum computing, why is this an advantage?
Well, this allows us to simulate more complicated structures. So quantum walks move around an environment that mathematicians call graphs. And these environments essentially become exponentially more complicated as you linearly increase the number of photons. So if I have one photon, it's moving through a system of, let's say, 20 waveguides, then my system is of size 20. Whereas if I stick 2 photons into the device, then I'm simulating a structure that's of the order 20 squared.
So, Jeremy, coming back to you, what do we hope to use these quantum computers for?
So these particular types of quantum computers based on quantum walks are in principle able to realise a universal quantum computer. So there's an exciting and important theoretical result to show that quantum walks are able to perform any sort of quantum computation. But in the nearer term, we expect to be able to simulate important quantum systems using these quantum walks in a sort of direct way. The types of things that we might be interested in simulating are complex molecules that might be relevant to designing new pharmaceuticals or new materials. And it turns out that if we have a molecule with of order 30 atoms in it, that's the limit of what we can reliably calculate on a conventional computer, even using a supercomputer today. And the reason is that the description of that system, it grows exponentially in the same way that Jonathan described the exponential growth of the quantum walk as we add more particles to it. Other applications include understanding natural processes like photosynthesis, which rely on quantum coherent effects for their operation.
So, by how much do you think your work has brought forward the reality of quantum computing?
So I think it's fair to say that the majority of people working in the field of quantum information science and quantum computing specifically believe that a universal quantum computer is decades away. But we're optimistic that using this quantum walk type technique, we'll be able to make a device that's able to do things that can't be done on a conventional computer within a 5-year timescale.
That was Jeremy O'Brien, and before him Jonathan Matthew, explaining how the phenomenon of quantum walk could help to lead to a revolution in computing. Their paper was published this week in the journal Science. As always, you can find more science news on our website at thenakedscientists.com/news.
Distilling the best science. The Naked Scientists.
You're listening to The Naked Scientists with Dave Ansell and with me, Ben Valsler. Still to come, we've got the very first edition of the new Naked Engineering segment. This one's looking at the strength and stability of an archway. You can tweet at Naked Scientists if you'd like to get in touch with us through Twitter. If you're a Facebook user, you can post a comment on our Facebook page, or as always, you can send an email to chris@thenakedscientists.com. The effects of climate change range from rising temperatures and higher sea levels to extreme weather and mass extinctions. If that wasn't bad enough, there's a hidden process that's already underway in the seas, and that is that the oceans are becoming more acidic. In the latest of our features from the Planet Earth podcast team, Richard Hollingham reports from the Plymouth Marine Laboratory, where scientists are investigating the effects of ocean acidification.
Steve Widdicombe's lab at the Plymouth Marine Laboratory is filled with tanks of water, from rows of deep baths in the centre of the room to a series of 10 tanks around the size of oil drums along the side.
In those tanks, we can actually change the chemical parameters of the seawater to mimic what the oceans might be like in 100, 150 years' time. And we do that by adding carbon dioxide. What we're trying to do is explore the effects of increased CO2 on marine ecosystems.
Kate Delahaye, for instance, is studying the effects of ocean acidification on the behaviour of hermit crabs. The crabs she's working on all live in periwinkle shells, and right now it's time for their lunch.
Well, with these hermit crabs, I'm looking at how their ability to pick up the odours of food is affected. So what I'll do is I keep them in certain treatments, but then periodically I'll take them out of the treatments and put them into an observational chamber, and then I'll put in food cues and see whether they can pick them up in the water or not. And also they have 2 pairs of antennae, and they have these shorter antennules which they flick through the water very rapidly. And it's like their sniffing response, and it helps them to pick up odours in the water, and it's quite easy to record that, so that's also what I'm recording as well.
We come out of the laboratory to a little bay just east of the main city of Plymouth, and with Nadia Kristen, who's got pan scourers in her hand. Why?
I'm looking at the effects of ocean acidification on rocky shore communities And what I do with these pan scours is basically these are community collectors. They mimic kelp holdfast, so loads of different invertebrate species will start to colonize these pan scours. So that's how we can actually collect the rocky shore communities I will need for my experiment.
So you'll put these on the rocks, they will mimic the base of the kelp, and you will collect, effectively, a community of organisms.
There are lots of studies just looking at one species, and the responses vary quite a lot between different species. So it's really difficult to predict how communities or even an ecosystem will respond to ocean acidification. And that's why in my study I'm looking at the whole community itself. So I want to look how the community as a whole responds to ocean acidification.
And back in his lab, I asked Steve Widdicombe whether he'd been surprised by what they'd found so far.
Often we are not getting the results we expect, and that the more we look into the issue of the effects of high levels of CO2 on marine organisms, the more we are astounded by the complexity of the responses that occur and the trade-offs that occur between different responses. For example, we've had an instance where a marine organism is seen to be unaffected by the exposure to high CO2. But as we look more closely, we've seen the fact that some of its muscles have wasted away because it's been using energy to respond to that. So whilst on the surface things look fine, underneath that's not always the case.
How important is it to get this sort of information?
Well, the information we're providing here we think is essential because, yes, ocean acidification is happening, and part of the effects we're seeing here will enable people to see the consequences of producing more CO2. But also it allows managers the opportunity to see how the oceans might be in 50 to 100 years' time. And whilst they may not be in a position to stop it, they are in a position to develop management strategies and mitigation strategies to be able to live with this change.
Steve Widdicombe from the Plymouth Marine Laboratory with Richard Hollingham. You can find the other Planet Earth podcasts presented by Sue Nelson and Richard Hollingham on our website at thenakedscientists.com/Planet Earth.
And now it's time for Naked Engineering, a new regular feature on the show where I join Mira Senthalingam out and about to find out the tricks and tools engineers use to solve real-world problems.
Welcome to Naked Engineering, where we strip down seemingly simple ideas in engineering and show the true complexities and the science behind them. So this week, for our first edition, we're going to be looking at a piece of architecture that spans far back into history and yet is a common feature of designs today, and that's the masonry arch. So to find out more, we've come down to the Structures Lab here at the University of Cambridge. Dave's here with me, of course, but also here with us is lecturer in structural engineering, Matt de Jong. Hello, Matt.
Hi.
Dave, you've got various things set up here, including many potatoes. So how are these going to help us understand about a masonry arch?
Well, basically you want to try and build one, and I thought a good material to make an arch out of, you need something which is fairly good at surviving squashing. Potato was ideal. You want to start off by making a square cross-sectional piece of potato. You want to cut it into really large chips.
Okay, so what you're doing here is you've cut it in half, then you've cut the kind of curved face off it again, and then sliced that flatter piece up into chips.
That's right. If you've ever looked at an arch, you've noticed that the bricks which make it up aren't square. The two sides are slightly chamfered, almost like a triangle with the bottom chopped off. So what we want to do is make a whole lot of bricks of this shape as close to the same as possible. Okay, so we're basically going to have to cut bits off this chip at an angle. About 15 degrees works really well. So I'm cutting one off at about 15 degrees, turning the chip over, cutting another one off, turn the chip over, cut another one off. Get a whole series of blocks which should be about the same.
Okay, and so Matt, Dave's been chopping away to produce 6 blocks. So what now to actually form our arch?
If you take the blocks and put all the tapered ends towards the middle of the arch, and then start building from one end, and when you place the last block in, they used to call that the keystone, because once you've placed that block in, the arch is now stable on its own, and you can release it, and hopefully it's standing.
Could you tell me a bit more about how this arch is actually working? What kind of forces are in play to keep it stable?
Right, so a masonry arch stands in pure compression, similar to a hanging chain would hang. If you held either ends of a chain, that chain would hang in pure tension. And if you invert that, the equivalent arch stands in pure compression.
You actually have a large chain here, actually, to show this.
Yeah, we do have a large chain. The shape that the chain naturally takes is called the catenary, similar to that of the arch if you flip it over.
So basically what's happening is this chain is hanging, and because the chain is flexible, if there are any sideways forces on it, the chain will move until there are no more sideways forces on it, so it's sitting nice and stably. And so if you turn that upside down, it means there's no sideways forces on an arch. And so the arch is nice and stable.
Yeah, that's right. And so the individual blocks within the arch remain in place because in order for them to slide out of the arch, they would have to push on the two adjacent blocks. And that's prevented basically by friction. The forces that are involved really is that the arch is acting primarily in compression. So the blocks are just pushing on each other. There's no tensile capacity because the individual blocks are free to separate from each other.
So if one were just to be pushed out of place, it would collapse?
Yeah, certainly. The arch stability depends on all of its members.
But now, in terms of showing just how stable this arch is, though, you've got a few more things you can do to it.
Yeah, well, the arch is remarkably stable under displacements at the base or at the point where the arch springs from. And so we can demonstrate that with the arch we have by taking the arch and holding it on either end and slightly spreading the supports apart.
Now, the blocks are actually moving quite a lot by moving the two end pieces out, but it's not collapsing. It's still actually staying upright.
Yeah, and so that demonstrates that under large displacements, the arch can still stand. You'll see huge cracks, probably, and maybe some sliding within your arch. Many buildings are still standing this way, including Clare College Bridge here in Cambridge, which, if you look carefully, is quite distorted because one of the supports on the end has settled quite a bit.
It's quite reassuring because it took me about 2 years to notice the fact that the bridge was completely wonky, despite having walked over that bridge several times a day, every day.
Now, what about the location of these arches? Commonly you see them, say, on top of cathedrals and things like that. Does that make it more difficult?
Well, yeah, it certainly makes it difficult because the arch thrusts outward, and so something needs to resist that thrust at the top of a cathedral, or else the building walls would push outward and the arch would collapse. We can actually build a model of that to investigate how the arch at the top of the cathedral might behave.
So we've got two big chips which can act like the walls of the arch. We can build the arch over the top of the two chips.
Okay, so the arch has just been put on top of two rectangular chips that are on either end, and is it going to stand? No, it didn't.
Yeah, so the two large chips on the sides were trying to act as buttresses, as they do in a cathedral, but our buttresses weren't quite wide enough, so the arch thrust outward, pushed those buttresses sideways, and collapsed into the middle.
So did cathedral builders build incredibly wide walls to take these sideways forces?
Yeah, they did, and if you notice on a building like King's College Chapel in Cambridge, they have buttresses along the walls, which are very thick, and that width is what's resisting that outward thrust from the arches.
And keeping it from collapsing.
Yeah, exactly.
This is your area of research, so do you actually then model these structures in your line of work?
Yeah, well, I'm particularly interested in the dynamic of response of these type of structures. So statically, we know quite well how they behave, but what happens to an arch, for example, if an earthquake hits? And that's a lot more difficult problem to solve. So yes, we build small scales of arches in the laboratory and then test them using a shake table to simulate real earthquakes.
What does happen then, say, with seismic effects, so earthquakes?
The dynamics of the problem allow the blocks to separate and come back into contact. So an arch behaves similar to a rocking block when an earthquake hits. The ground moves back and forth sideways. Then the arch will begin to rock. And a mechanism forms where the arch sways in one direction and then sways in the other direction, back and forth. And if the ground motion is large enough, then obviously it would collapse. But in our experiments, we do find that the arch still is remarkably stable under that type of loading.
Okay, so there's actually a lot to the arch. It's not just the aesthetics. So the next time I walk past one, I think I'll appreciate it quite a bit more.
Yeah, that's right. It's a form of construction that's been around for quite some time, over 2,000 years, and partly because it's an extremely efficient way to build and an extremely durable way to build.
That was structural engineer Matt de Jong showing Mira and me the strength and stability of arches. Naked Engineering is supported by the Royal Academy of Engineering, and we'll be back next week looking at the science and engineering of superconductivity.
Now, thinking of compression and compression forces and that sort of thing, we've had an email question from Jim Irvin, and he wants to know if you can compress water into a solid. Now, obviously, you can turn water into a solid just by taking heat away, but can you just press it hard enough to make it into a solid structure? Dave, what do you think?
The simple answer is yes, you can. You need a really ridiculous force because it actually forms a form of ice called ice 7, which is a different structure to conventional ice. It's got less space in it. It's not the kind of hexagonal structure of conventional ice.
Conventional ice is larger. It has a greater volume than water, so compressing water, in order to turn it into conventional ice, you'd need to somehow compress it into a solid and allow it to expand.
Yes, it just wouldn't work. It's still exactly the same stuff. It's still made out of water. You need a pressure of about 2 gigapascals, which is about 20,000 atmospheres, or the pressure you get under about 2 kilometres of ice or water. At that point, you can produce ice at normal room temperature.
Are there any bits of the world where water is under that sort of pressure, 2 kilometres down, deep in some of the deep ocean ridges? And if so, why doesn't it form that ice structure?
There is that pressure down there. There's quite a lot of salt in the water down there, and it's probably still not especially stable. Although down there you do get strange structures, things like methane hydrates, methane clathrates, which was actually a big problem with the Deepwater Horizon thing, where you get ice forming around methane molecules, and these forms this ice thing and stores huge amounts of methane. In fact, probably a large proportion of the natural gas in the world is stored in these ice structures at the bottom of the oceans.
So water seems like such a simple thing, such a simple everyday thing, but actually it's fascinating stuff, isn't it?
Absolutely bizarre stuff.
This is The Naked Scientists with Dave Ansell and with me, Ben Valsler. Coming up, we'll find out why your idea of a good night's sleep might have more to do with our culture than our physiology. And Diana O'Carroll will ask if olive oil is better for you than butter in our question of the week.
If you'd like to contact us through Twitter, it's @NakedScientists, or you can send us an email to chris@thenakedscientist.com.
This last week has been the British Science Festival based in the city of Birmingham. The events there covered the full range of sciences, technology, engineering and maths. And one event even celebrated Pi time. That was 3:14 p.m. on the 15th of the 9th month. 3.14159. It's the closest you can get. And I'm sorry, in America, that one's just not going to work. So Julia Graham met Robin Wilson. He's Emeritus Professor of Pure Mathematics at the Open University to find out a bit more about pi.
'Tis a favourite project of mine, a new value of pi to assign. I would fix it at 3, for it's simpler, you see, than 3.14159. That number 3.14159, of course, is not the exact value of pi. The exact value of pi, no one knows. It's a number you go on writing forever and ever. So what is pi? We all learnt about pi at school. It's to do with measuring circles. First of all, it is the ratio of the circumference of a circle to its diameter. We all know the formula of circumference is 2 pi r, where r is the radius, which is the same as pi times the diameter. But we also know that pi comes up in the area of a circle, pi r squared. But trying to find the value of pi to more and more degrees of accuracy is something that mathematicians have been trying to do for 4,000 years. So the earliest were the Egyptians, and the Egyptians had a value which was actually 256 over 81. That's about 3.16, which is just a little bit too large.
Do you know how they arrived at that number?
Yes, they regarded the area of a circle as approximately the same as an area of an octagon. They found that what they should do to work out the area of the circle, they take 8/9 of the diameter and square it. Then that gives you the area of a circle, and that corresponds to about 3.16, which is a little too large, but not much. But the real breakthrough came with the Greeks. We all know that the ancient Greeks really launched mathematics. Archimedes, who of course is well known for many, many things, he was interested in finding the value of pi, and the way he did it was he drew a circle, and he drew a hexagon, he put it inside the circle, and he did another hexagon outside, and then he measured the perimeter of the hexagons. So the one inside gave him a value of 3, and the one outside gave a value of about 3.4. So that tells you that pi, the circumference of the circle, lies between those. Well, that's not very accurate. So he then replaced the hexagon by a dodecagon, In other words, he multiplied the number of sides from 6 to 12, and that gave him a better upper estimate and a better lower estimate. Still not very good, so he went up to 24, 48, 96. And he stopped at 96, and his calculation showed that pi was a little bit less than 22 over 7, and a little bit more than 3 and 10/71. But basically that gave pi to 2 decimal places, 3.14. And then for the next 2,000 years, people used the same method, exactly the same method. In 1596, a German mathematician living in the Netherlands called Ludolf von Ceulen went up to 2 to the power 62 sides, basically millions and millions of sides. And he found pi to 35 decimal places, and he was so thrilled with this that he instructed that those pi to 35 decimal places should be inscribed on his tombstone.
What is it that still fascinates mathematicians today about pi?
If you give me any pattern of numbers, like 6, 4, 8, 2, 3, 5, 9, for example, I just made that up now, we believe that any pattern of numbers like that you'll find it somewhere in the digits of pi. We don't know that. That has never been proved. And this is why people try now to find pi to more and more decimal places. I mean, if you want to study practical problems, you probably don't need to go for more than about 5 or 6 decimal places. But on the other hand, if you want to find out what pi is all about, is it true that every pattern of numbers that you give me appears somewhere in that list? So that's one of the fascinating things that people don't know the answer to.
How many decimal places do we know pi to now?
In 2002, a Japanese mathematician called Kanada reached 1 trillion. And then just last month, August 2010, we've reached 5 trillion. No practical use whatsoever, but why do you do it? Because it's there. It's like climbing mountains.
Professor Robin Wilson there explaining why understanding pi is a bit like climbing a mountain. Unfortunately, that gave me images of mountains of pi, so I'm now very much looking forward to my dinner. He was talking to Julia Graham.
Now, there are many different types of arthritis, and it can be caused by infection, trauma, autoimmune diseases, or just simple wear and tear with age. One of the more common forms is rheumatoid arthritis, but if you diagnose it early enough, it can be controlled well with drugs. Sadly, rheumatologists often don't see these cases until a long time after the onset of symptoms. Karim Raza, senior lecturer at Birmingham University and consultant rheumatologist at Sandwell and West Birmingham Hospitals, explain more.
So rheumatoid arthritis is a common arthritis. It affects 1% of the population, and it's characterized by inflammation of the synovium. The synovium is a very thin layer of cells which lines most joints, and it produces the synovial fluid, the lubricating fluid within the joint. In people with rheumatoid arthritis, that synovium becomes inflamed. It becomes thickened. As a result of that, people get pain, stiffness in the joints, and most importantly, that synovium actually eats into and destroys bone. So in the long term, it causes damage and destruction to the joints, which is irreversible actually once the destruction has happened, which is why it's important to catch people early before the damage sets in.
How does it affect quality of life? Obviously, living with pain is not pleasant, but a lot of the time people find ways to cope. How does rheumatoid arthritis affect people's ability to work, for example?
It has a huge impact on function. So within 5 years of a diagnosis of rheumatoid arthritis, about 25% of people will have lost the jobs that they were in, and a proportion will clearly also be functioning much less effectively in the jobs that they're in. So it does have a very big impact on function and quality of life.
What are our treatment options at the moment?
Treatment options that we have when we first see patients with rheumatoid arthritis are with drugs which modulate the immune system. So we want to dampen down the inflammation in the lining of the joint. And the most commonly used drug at our disposal is a drug called methotrexate. If you don't respond to methotrexate, we add in other oral drugs. And if you don't respond to those, which takes you down to about 10-20% of the rheumatoid population, then we have to move on to stronger drugs which have been designed to specifically target particular components of the immune system.
Is it important to catch it as early as possible?
All the data that we have available suggests that the first 3 or 4 months after the onset of symptoms is a really critical time, and that if you can intervene at that stage, you can really slow down the rate of progression of disease.
So what are the factors that are limiting early treatment at the moment?
One of the key factors that's limiting early treatment is the fact that we don't get to see our patients in our rheumatology clinics as early as we'd like. And if you think about what the determinants for delay are, say you develop inflammation in your joints, you'll spend a little bit of time deciding what to do about it and whether to go and see your GP. Then your GP will spend a bit of time deciding whether to refer you to the hospital, and then you'll get stuck in a hospital waiting list somewhere. So there's 3 levels of delay. And actually, when people have looked around the UK at those 3 levels of delay, the main reason for delay, in fact, is delay on the part of the patient. So if I told you that the average delay for a patient with rheumatoid was 6 months from when their symptoms began to when they saw a rheumatologist, if you break that down into the 3 components, 3 months tends to be delay on the part of the patient, and the other 3 months is split between the delay on the part of the GP and the hospital. So the patient is accounting for the largest bit of it. And patients delay because they don't know anything about rheumatoid arthritis. They have no idea that it's a serious disease. They have no idea that there's treatment available for it. They have no idea that early treatment is important. In fact, when we've asked our patients, the vast majority have never even heard of rheumatoid arthritis.
So what should people look out for? How can they tell the difference between an ache, a pain, perhaps a bit of swelling because of minor trauma, and something that they do need to go and speak to their GP about?
So there are a number of key features in the story that we look for when we take a patient's history, and these are the kind of things that patients should be looking for. And the first of them is morning stiffness. Often our patients are stiff for at least an hour in the mornings. They start easing up as they start using their joints, as they start doing things, but they're very, very stiff in the mornings. I'm not talking about the 2 or 3 minutes of morning stiffness, which you probably all feel when we roll out of bed. It takes us a few minutes to get going. This is morning stiffness that lasts for at least an hour. The second thing is what joints are affected. So rheumatoid typically begins with the knuckles and the small joints of the fingers, the wrists and the small joints of the toes. So patients may well notice pain, swelling and stiffness in the hands and in the feet. So it's the morning stiffness and the pattern and distribution of joint problems which are key features of a new onset of rheumatoid arthritis. And anyone who has those should really be going to see their GP.
That was Karim Raza on the symptoms that suggest rheumatoid arthritis and how the biggest problem with catching it early is actually the patients themselves.
And this is definitely worth you thinking about, because something else that Karim said to me off mic was that having rheumatoid arthritis actually greatly increases your risk of heart attack, because chronic inflammation tends to lead to these systemic problems. So if you do think you have those symptoms, if you do get stiffness for an hour in the morning, it's well worth going to see your GP. And now, speaking of the mornings, what constitutes a good night's sleep? Here in the UK, we're told that it's solid 8 hours overnight, tucked up in bed in the dark and in the quiet. But if we don't do that, or if we can't do that, we're thought of as being unusual. Margaret Thatcher, former Prime Minister, being a very good example, said to only sleep 3 hours at a time. Or we're told that we have a sleep problem. Helen Ball, Professor of Anthropology at Durham University, is looking into the cultural aspects of sleep.
We're interested in the mismatch that happens between our evolved physiology of sleep and the way in which we sleep in modern Western societies. So we're looking at things that we think of as sleep problems in our society, that when you look at sleep habits across the world are actually normal human sleep patterns.
We are fairly well conditioned to think that we need to go to bed at a reasonable time, get 8 hours solid sleep in one block, and this obviously fits around work or school or our lifestyle. Is that backed up by good science? Is that physiologically a healthy way to sleep?
Well, that's how sleep has been studied in sleep laboratories, because that's the model of what good sleep is in the Western world. But if you look at historical reports, there's an interesting book by a guy called Roger Ekirch called At Day's Close, and he looked at a lot of diaries from between 500 and 200 years ago, and he found people talking about how they would have what they call a first and a second sleep. So you would go to bed at twilight, you would spend a couple of hours relaxing and kind of winding down, you'd sleep for 4 or 5 hours, then you'd wake up, and you'd have what was called a watching period, where you were kind of quiet awake for a couple of hours, and then you would go back to sleep for another 2 or 3 hours. And it puts me in mind that some of the problems that people think that we have with insomnia, and the insomnia epidemic that we supposedly have in the Western world, is actually an artificial creation of trying to force ourselves to sleep for a solid block when actually physiologically that's not what our bodies expect us to do. Another issue is trouble falling asleep in the evening. And there's a lot of sleep hygiene advice out there about what you should do if you're having trouble falling asleep. And some of it makes a lot of physiological sense, like staying away from things that act as artificial stimulants like computer screens and TV screens and obviously caffeine and stimulant drinks and all the rest of it. There are other things about sleep hygiene that are really just culturally conditioned. If you think about how people would have slept throughout history and do sleep around the world, they don't sleep in soft, comfortable beds and they don't sleep alone in silent conditions, etc. And so we've entrained ourselves to expect this very kind of rigid and constrained sleep environment. In some respects, we're setting ourselves up to have these sleep problems. And one of the things that I've studied the most is the sleep of infants and the way in which we expect infants to sleep. And parents start out by trying to teach their infants to sleep for long periods of time in dark, quiet rooms, and they tiptoe around them so they don't wake them up. But babies all around the world sleep in hugely social, noisy environments being carried around, etc. So babies can do that. There's no reason our babies can't do that. We don't have to teach them that the only way to sleep is in a silent room with the lights out, with a very comfortable, warm bed.
It's also true that the amount that we sleep, the amount we need to sleep, and the times that we need to sleep change quite dramatically throughout life.
Well, this is another good point. Historically, over the last 50 or 60 years, we've tried to get children to do what we call settling, which is starting to consolidate their sleep into nighttime chunks earlier and earlier and earlier. And so people now are trying to sleep train 3-month-old babies, and 3-month-old babies physiologically aren't ready to have their circadian rhythms entrained in that way. But children do need a much greater amount of sleep than adults do. But if you do a survey of how much children sleep, it ranges anywhere from 9 hours to 15 hours. So there are biological differences in people in terms of how much sleep they need, but then there are also differences in the ways in which the amount of sleep your body needs can be obtained in a 24-hour period. One of the things that we've found in interviews with parents is that they're very resistant to the idea of children having naps during the day in UK culture, because they think if children have naps during the day, they'll stay awake at night. But if we look again at other societies, and even the US, there's a very familiar culture there in kindergarten of children having naps in the middle of the afternoon.
And just lastly, do you think we should try and change our society to fit our sleep needs? Should we have no early morning lessons for teenagers and the ability to flexi time at work in order to suit our own sleep patterns?
Well, the idea of later starts in the morning for teenagers is a very popular one, and it's been done in some schools in the States, and it does seem to have made a difference to academic performance. And there is some evidence that teenagers' sleep patterns do undergo a shift so that they do biologically sleep later, go to sleep later and wake later. So it makes sense to do that. But yes, I think the idea of people being able to incorporate their work lives around their sleep needs is a very good one. So more flexi time would be an excellent idea.
That was Professor Helen Ball. She's investigating how our culture can affect our idea of a good night's sleep. And I'm sure there are lots and lots of teenagers who would instantly vote for the idea of no lessons in the morning. I certainly would have done back when I was sort of 16, 17.
I don't know about back when I was 16, 17. I think I would do now. Now, another important aspect of science festivals is the diversity of people, interests and talents coming together to celebrate science. The festival saw science, art, maths explained through juggling and an event of science-inspired poetry.
My name's Heather Wasty, and my poem is about one of the first people to work as a forensic pathologist. His name was Sir Bernard Spilsbury. Holy Harvey Crippen said his wife, called Belle, was missing. Said she'd gone off with her lover to some place or another. And the body beneath his cellar, well, he said it wasn't Belle. A lie, so it was proved, when Bernard Spilsbury entered the case, with his little black book, index cards and the acrid smell of formaldehyde, immersed in his work with very few friends, unemotional, clear in mind. A quiet, solitary, dignified man, polite, reserved, he worked alone and came alive in the cutting room. With a woman who died of a dry shampoo, or little Louisa poisoned by rhubarb, the man who had told his poor grieving mother that something was wrong with his private parts, or Ada, a laundress with 4 young children who swallowed quinine dissolved in port wine at 9:15. failed abortion, suicide, poisoning with arsenic, matricide, doping to render unfit for war, sadomasochist, blood and gore, harikari by Japanese, and other gruesome jobs like these.
That was poet Heather Wasty at the British Science Festival's stand-up poetry evening.
And I must say that not all of the poems were quite so gruesome. Dave, we have had a question from Ryan in Cambridge, and he said, please tell me why a fridge's magnetic door seal is harder to open just after it's only just been closed. I'm guessing he means rather than when it's been closed all night.
That's right, it's a lovely piece of physics, this one. Basically, the magnetic door seal, it kind of clips on and it makes a really good airtight seal. That means that the fridge is full of fairly warm air from outside. Then, over the next 2 or 3 seconds, that cools down. When air cools down, it shrinks. So that reduces the pressure inside the fridge. So to open that door now, you've got to pull against all that pressure difference, and it's really difficult. But if you leave it for a couple of minutes, and there are a few leaks in there, so the air slowly works its way back in, the pressure's equalised, so it's nice and easy to open again.
Fantastic, Ryan. I hope that answers your question. You're listening to The Naked Scientist with Dave Ansell and with me, Ben Valsler, and we're looking at some of the interesting things that happened at the British Science Festival this year. Science festivals are a very good chance for scientists to meet the public face-to-face and find out how their work affects other people. But when it comes to controversial experiments, it's important to understand both sides of the coin. Why do the scientists think it's necessary? And why do the public have a concern about it? Now, Robin Lovell-Badge is from the National Institute for Medical Research, and he's been researching public opinion of animal experiments that have a key biological human element, as he explained to Smita Mundasad.
It began really because of the debates around the Human Fertilisation and Embryo Act, where we were talking about issues of combining human and animal material in the context of human embryos, so making hybrids, interspecies hybrids and things like that. It became apparent that certainly members of Parliament and some members of the public who asked questions about this didn't realise the extent to which research is already going on doing the other way around, so having animals where we're introducing human material. So that can be to put human genes into animals to make so-called transgenic animals, transgenic mice, for example. And there are many thousands of examples where we now have made mice carrying a human gene, now all the way up to a whole human chromosome. The Downs mouse is a model of human Down syndrome, where a human chromosome 21 has been added to the mouse genome. And then the other type of manipulation is where you put human cells into an animal to make a chimera, and the different ways you can make a chimera. It can be done from early embryonic stages all the way up to adult animals, where you introduce human stem cells from the nervous system into stroke-damaged rat brains, for example. And so all this type of research is going on quite happily, and everyone seems to be generally happy with it. The question is, should there be limits? What are the issues when you start putting, for example, a whole human chromosome into a mouse? Would that be something that we should be worried about, scientifically and ethically?
What have you done so far to look into where to set the limits or what the public thinks about it?
The working group has basically been taking evidence from a wide range of people who may have an interest. And then we've also had a public engagement exercise. And in general, the small sample of the public seemed, on the whole, really very accepting, but they were pragmatic. So if it had some obvious medical benefit, not necessarily immediately, but it was going to lead to something, they had no problems really, almost whatever our scientists did.
Were there any particular types of research or experiments that the public were not so happy with?
They didn't seem to have any limits. The areas of research that they had most concern about were those involving particular organ structures, for example, the brain and the reproductive system. The brain, in particular, changing behavior of an animal in a way that it would no longer be the original animal, or, and it's very unlikely this will ever happen, that it started acquiring human characteristics. And then, I guess, the reproductive tissue, so whether you have animals that are able to produce human eggs or sperm, people are a little concerned about that. Although when told what the reasons why people were doing this, they could accept it. So providing some context for the research makes people much happier to accept it. Essentially what that means is it puts the emphasis on the scientists who are doing this type of research to justify their experiments.
The MRC's Robin Lovell-Badge explaining how understanding the context and the aspirations of controversial research makes people much more accepting. And this highlights the need for scientists to be more proactive in explaining their research.
And now let's join Diana O'Carroll for our question of the week.
This week it's time to oil up some naked scientists with a question from David Karma.
Hi. For quite a few years now, we've been using olive oil-based butter in our household because we've heard of claims that since olive oil is healthy, then its butter and margarine-based counterparts are healthy as well. Does the claim still hold true that olive oil-based butter and margarine are healthier than their dairy or coconut counterparts? Thanks.
Is olive oil really better for you?
Good afternoon. My name is Brian Lockwood. I'm a professor of pharmaceutical sciences at the University of Manchester in the School of Pharmacy. Olive oil's obviously got a long historic use in both food, and the olives have been eaten for a long time. By now, of course, there's plenty of other dietary oils which we use as well. The recent increases in interest in health in westernised countries, particularly those in the northern hemisphere, has stimulated a vast amount of interest and research into the fat content of our diets. And linked to this, there's an increasing volume of epidemiological evidence which suggests that dairy and animal fats are less healthy. And this is now pretty widely understood in the medical fraternity and also in the general public at large. The main reasons why olive oil is supposedly beneficial for you is that the main lipid is oleic acid or oleic acid triglyceride, and it's about 3/4 of that. And this is a particular type of fatty acid which is unsaturated. In fact, it's a monounsaturated fatty acid which is accepted as being good for health. There's also some polyunsaturated fatty acids, which of course have been widely discussed in the lay literature as well. Again, highly beneficial for your health. Both olive oils and seed oils in general have been shown to reduce low density lipoprotein lipid cholesterol, which is abbreviated to LDL-C. This is commonly referred to as the bad type of cholesterol. Total cholesterol is also reduced. The combination of these two activities generally reduces the possibility of cholesterol depositing in the arteries.
So olive oil is lower in saturated fat, and the more olive oil is in butter or margarine, the less dairy fat will be present, and therefore less saturated fat. Our expert added that olive oil also contains higher levels of antioxidants, and that these prevent free radicals from running around inside your body and damaging cells. But there's no conclusive evidence that antioxidants, when taken via food, actually make that much of a difference. But some people say olive oil is less healthy when you fry it. Why might this be?
Olive oil is quite interesting. Due to the high level of polyphenolics, you can actually see in the case of virgin oils and extra virgin oils, it's a green to dark green colour. This is judged to be of quality by the food salespeople. If you happen to heat olive oil in a frying pan or a pan and get it up to about 93 degrees centigrade, it smokes. And this is obviously degradation of the oil. So it's not beneficial to burn the olive oil itself. And in fact, this destroys its properties later on. So its antioxidant activity is dramatically decreased.
So there you are. Olive oil smokes slightly earlier than other oils. But if the clinical trials are anything to go by, it may be that losing a few antioxidants isn't a great loss. Next week, we've another question about diet that gets right to the core.
Hi, my name's Hannah. My friend the other day told me not to eat my apple core and made me throw it in the bin. I was wondering why. Are they poisonous?
Should you throw away your apple cores or devour their lignin-y centres with gusto? Let us know what you think by writing on the forum at thenakedscientists.com/forum or by emailing chris@thenakedscientists.com.
So what do you think? Are apple cores dangerous, or is throwing them away just a waste of a good apple? Dinah will be back with the answer next week.
But that's all we have time for this week. Next week, we'll be having a look inside our heads to find out what it is that brain imaging can tell us. If you've got any questions or comments for us, you can email chris@thenakedscientists.com. You can tweet at Naked Scientists, or join us on our Facebook page. As always, there's also the forum where you can ask and answer questions. That's at thenakedscientist.com/forum. Many thanks to our production team this week. There's a lot of them: Sarah Costa-Perry, Tom Simpkins, Diana O'Carroll, Julia Graham and Smita Mundasad, and of course Mira Senthalingam presenting Naked Engineering. The Naked Scientists was produced and presented by Ben Valsler, Dave Ansell and Chris Smith. It was produced in association with the Open University. To discover a whole range of science content, including lots of interactive features, log on to thenakedscientist.com and follow the links to the Open University.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the Natural Environment Research Council and UK FAST. For more information, look us up online at thenakedscientists.com.